What is permutation? Permutation is nothing but arranging distinguishable things in a particular order. Let us say we are we are given the task of arranging 3 distinct balls in 3 boxes in a very specific order. I have box 1, I have box 2 and I have box 3. These 3 boxes are there and I have 3 distinguishable balls. I can put one of them in one box, one of them in second box and one of them in third box. Note that I cannot have more than one ball in a box. Okay. In this kind of situation, what will be my statistics? What will be the number of possibilities? So, first box can be filled by any of the 3 balls. Okay. That is the first thing. I have these 3 balls, right, red, green and blue, and I have 3 boxes also, and these boxes are very distinguishable boxes. You see, I have numbered them 1, 2 and 3. First ball I can put in any of the boxes, or rather let us say first box, box number 1 I have to fill up. I can pick up any of the ball. Let us say I picked up a green one, a blue one, sorry. If I picked up the blue one, I will be left with red and green. So, this is 3 ways I can do that, right. And then since I am not doing with replacement, my blue is gone. I have only 2 balls now, red and green. For the box number 2, I will have to choose one. I choose red one. So, I can choose 2 ways, either red or green, but then last case I am left with only one, and that is a green ball. So, number of possibilities will be 6 as I mentioned here, or we can say also as factorial 3. Factorial 3, factorial n is typically n into n minus 1 into n minus 2 till 1. So, you see, if I have n balls, n distinct ball and n distinct boxes such that I can put only one ball in a box, I can do that in factorial n number of ways. That is called permutation. Permutation is nothing but arranging distinguishable things in a particular order. For example, I am giving you 3 letters A, B and C, and I am telling you that how many possible words you can make, of course meaningless words. Let us say how many possible words of 3 letter can you make. So, you can take any of the first 3, then any of the second 2, then the last one you have to take. So, then again factorial 3 ways you can do that. If I tell you that okay, you have A, B, C, D, how many 4 letter word you can make out of this? Factorial 4, because you can make in any combinations. You can take any of the 4 as the first letter of the word, then you can take any of the other 3 as the second letter of the word. Only condition here is that you are always picking one, not more than one, just like you are putting only one ball in a box, not more than one. And you see, you have a very nice arrangement here, blue, green, blue, red, green arrangement. You could have red, green, blue arrangement also. You could have green, red, blue arrangement also. In fact, all possible 6 possible arrangements you could have had with that, and that is what is called permutation. Permutation is actually making distinguishable things in an order, and how many such things will be possible. Now, when you look at this particular configurations of blue, red and green, you immediately see that as one configuration. We can say that as one microstate. I change that combination, I get another microstate. I change that combination, I get another microstate. How many possible ones? 6. After the 6 is just going to repeat it. If it repeats, it is no longer of any use, right. So, because we are no longer we are going to count it. It is almost symmetry and group theory, symmetry measurement. So, when you rotate something, when you rotate 360 degree, it will become the same one. So, you do not have you cannot distinguish between the initial one, or when you rotated it full 360 degree, you cannot distinguish between them. So, therefore, every system will have that is called C1 symmetry, in which you rotate 360 degree and you will not have anything, at least C1. There can be even more, where by rotating less also you can get that, but that is a different topic altogether. Now, let us do a little bit more complicated. Let us say I have only 3 boxes, but 6 balls. The 6, all 6 are there here, and I have only 3 boxes just like above. How can you do that? So, first one can be again taken, let us say I have the 3 boxes. So, first box can be filled by 6, any of the 6 balls, but once I feel that it is without replacement, remember I am left with only 5, then I am left with only 4. So, how many possibilities I will get? 6 into 5 into 4, which is 120 possibilities. So, 120 microstates I can create from these 3 boxes when I have 6 balls available with us. And this situation, as I said, that permutations are also sampling without replacement. Same thing, I am from the pool of these boxes, from the pool of these balls, I was putting them in the boxes. In fact, I need not have put it. When I am picking up for the first time, it can be my first box. When I am picking up the second time, it is my second box. When I am picking up the third time, it is my third box. So, only taking out itself can be thought of as a permutation. So, permutation are also sampling without replacement. See, without, with replacement gave us to the power n to the power r, but with replacement is giving us what we will see. Put r ball in n cell without replacement, such that one cell, a cell can have at most one ball, at most. That is very important. Why? We will come back in a moment. So, as you see that now I have 7 boxes, 7. I said at most, right? Why did I say at most? At most. You see, this is very important. Why I say at most? Because if my number of boxes is greater than number of balls, then all the boxes will not be filled, because I can put at most 1. So, it can be 0 or 1, all are distinguishable balls, all are distinguishable boxes. So, how many ways we can do that? So, again, as you can see that my first box can be filled in 6 possible ways, second box can be accordingly. First box, let us say I have now n boxes, right, and r ball. So, my first ball can be put in any of the n boxes. My second ball can be put in any of the n minus 1 boxes. Third ball can be put in any of the n minus 2 boxes, and then like that I have r terms, because I have r balls. Only thing is that if let us say n greater or equal to r, let us say if n would be less than r, what will happen? If n is less than r, that means boxes are less than, then I must have to put more than 1 ball in a box. That situation will arise, but I have forbidden that. So, this is not allowed, n less than r is not allowed. So, you see this situation where I am choosing any of the n boxes for my first ball, and then I am left with only n minus 1, because I cannot put more than 1 ball. So, n minus 1, and then my third box will have n minus 2, and like that I have r balls, so r terms, and that can be written as factorial n by factorial n minus r, because factorial n by factorial n minus r is exactly that one, if you can think of. For example, let us say, let us talk about n3 and r1. So, n3 and r1 is just 3, because I have only 1 boxes, right. So, that can be written as 3 factorial by 3 minus 2 factorial, sorry 3 minus 1 factorial, because r1. So, it is 3 factorial by 2 factorial, and 3 factorial is written as 3 into 2 into 1, 2 factorial is just 2 into 1, cancels and give me 3. So, this n factorial by n minus r factorial is called NPR, permutations of n particles into r, or n into r levels. Okay. So, this is a particular situation in which permutation is required, and we can get an estimate of number of microstates. So, now you are getting a hang of things, that when I am talking about a microstate, this is a distinguishable configurations of distinguishable things. It can be particles, it can be balls, it can be dice, it can be coins, it can be anything, as long as I distinguish it. In the context of chemistry, of course, we need something more tangible, like particles, like molecules, but this is this probabilities is not restricted to chemistry. It is it is mathematics, it can be applied anywhere else, and therefore, whenever we want to connect to a situation, we can always associate probability, and if we want to call that entropy, that is us to do that. For example, we can say that entropy of getting 2 different colored cards out of 4 cards in one hand is more. What we are saying, that the probability is more. So, entropy of the situations in which we can put distinguishable balls in distinguishable boxes will be more. We are all saying that basically the possibilities are more, they are equivalent. So, entropy is nothing but, as I said, options or possibilities. Possibilities give us probability, more possibility is more probability. So, these words are connected. Probability is a word that is associated with mathematics of calculating a ratio, that how many possible ways I can get something out of all possible ways, that is the probability. So, now probability will increase when the numerator will increase, and numerator is how many possible ways we can get certain things, which will decrease when the number of possibilities increases in the denominator. So, you see that we will see that it is not even the it's for a particular thing that we want to get, the probability becomes important. Even without probability, the all total possibilities, if it increases, that also will increase the entropy. Will be more clear later on this aspect, but now we understand what permutation is. Now we will switch to more than one ball in a box. Till now we were concentrating ourselves to one ball in a box, but still we are still talking about distinguishable particles. Okay. Now we will see that if we have more than one ball in a particular box, then what kind of situations we will get. We will see that it will be something called combination rather than permutation, and combination is a choice, we have to choose. So, what is the number of possible combination of R objects from set of n objects, or you can say R balls from n balls. And so, these are the typical example of 6 balls, and that we have to choose. Out of that, let us say choose only 3. So, our R equal to is 3 and n equal to 6. In that situation, we write that n choose R, and let us say we have only one box. In that we have to put 3 balls in one box, because see, remember we were saying earlier that we have to put one ball in a box for permutation, but now in combination we can put more than one ball. So, initially they are all distinguishable. Once we put in the box they are all indistinguishable. Okay. So, we have to put 3 balls from out of 6 balls in the box. So, how many possible ways you can choose? We can choose in something called n choose R or NCR ways, which by formula is factorial n by factorial n minus 1 n minus r and factorial r. You see, in that case I have an extra r factorial on NPR. So, I had an NPR which is permutation. On top of that I have divided that NPR by factorial r. Why we did that is because when I am choosing this one ball out of all possible 6 balls, then I can pick any one of them, what do you say, I can pick the first ball in any 6 ways, I can pick my second ball in 5 ways, I can pick my third ball in 4 ways. That is nothing but NPR or 6P3, right, that we discussed. But once I choose my 3 ball and I put them here, they are all indistinguishable. In the same box they do not have a separate identity. We do not care which came first, which came later, we do not care about that, as long as they are there. And that situation says that there are factorial r number of ways I can distribute them inside the box, which are all equivalent. So, this is factorial r. Factorial 3 is nothing but 6, right. So, these are, let us say I have chosen this green, blue and brown ball, grey ball, green, blue and grey. let us say I have chosen out of the 6 possibilities, and but these ones, all possible configurations are equivalent when I put in the box. So, therefore, I have to divide by that, and that is the division of 1 by factorial r that I mentioned, and that reduces the number of configurations by factorial r. So, therefore, this choice that we talked about, that reduces the number of possible microstates, because we do not care about which particle, which ball came first and which ball came second and which ball came third. Once we do not care about that, we have factorial 3 ways of doing that, and therefore, from permutation we are getting a sense of combination that from permutation, if you divide by the number of balls that are grouped together, then that will give us combination. So, combination means you combine things. So, you combine 3 balls and give them a single label, just like what is mentioned here. So, 63s are 6 into 5 into 4 divided by factorial 3, and that becomes only 20. So, how many ways 6 balls can be chosen from a box given? So, now let us say I have to choose all 6. What will be the number of possibilities? All 6 I put in one box. There is only one way of doing it. I have to take all of them and put it. There is no other possibilities, and that is happening because I put 6 factorial on the numerator, but I divide by 6 factorial back again when they are put in the box. Then they become indistinguishable. So, all 6 of them are inside the box and they are all indistinguishable. They lost their color, which is seen here. Now, in the box they lost their color. So, there is only one way of doing it, and that is what combination is. And we will see later on, when you put particles in labels, in a single label, particles have no distinguishability. Before that, when you choose them, there is, but in a single label they do not care that which particle came first and which particle came later. Therefore, all of them are indistinguishable in the same label, in the same box, and that gives us combination. So, combination to permutation, we have discussed that how many ways 6 balls can be chosen from 6 boxes such that there is only one particle in a box. One particle in a box, that was permutation. So, if I just put one particle in a box, it will go back to the permutation. When you combine them, that gives us combination. Now, let us look at a different situation. Now, balls are indistinguishable, but cells are distinguishable. Earlier, both balls and cells were distinguishable. Now, we are coming to a situation where balls are indistinguishable. So, earlier we had 3 balls like A, B and C. We can call them all A, or we can call them all stars. Next will be indistinguishable. Boxes are still distinguishable by, so I have 3 balls of, they are all indistinguishable. I do not have any color anymore, but I have these 3 particular boxes. Now, how many ways do you think it is possible? This is a typical problem of star bar problem. We will show you that later on, but now we are just going to enumerate it in a different way. I will show you, because this number is smaller, we will show you here all possible combinations, but in future for any general combinations of choosing R indistinguishable balls for N distinguishable boxes can be done later on. Now, look at these possibilities here. I denote the balls as stars and boxes as these spaces. So, this is box number 1, you can say this is box number 2 and this is box number 3. So, I have 3 boxes and I have 3 balls as stars. Now, how many possible ways can be done? You can see that I can put this 5 plus these 5 possibilities. As you can see here, that 3 particles in that box is fine, in first box, 3 particles in second box is fine, 3 particles in third box is fine, that is okay, that is not a problem. But earlier I had another situations. So, for example, here I have 2 particles here and 1 particle here. Now, earlier I had more situations here. I had A B and C, I had A C and B, I had B C and A. But they all collapse to only one possibilities, because if they are all star, then it is same as star star star, this also will be star star star, this also will be star star and star. See, now these three are indistinguishable, right? We cannot distinguish this from this from this from this, we cannot distinguish it. So, therefore, when the balls are indistinguishable, we reduce number of microstates, we get less number of microstates, and that is why from 27 we got only 10 possible distinguishable configurations. From, for example, look at here, I have 3 stars here in 3 different boxes. Earlier I could have many more ways, I could have A, B, C, C, B, A. In fact, I could have 6 possibilities, A, C, B, and C, A, B, and B, A, C, and B, C, A. Did I write all that? Yeah. So, all those 6 possibilities now are nothing but star, star and star. The 6 possibilities collapse to only one possibility. Here 3 possibilities collapse to, I do not know that there can be more possibilities than the 3 actually. So, I can take, this was any 3 of the ways, no, 3 possibilities. So, these 3 possibilities collapse to only one possibility. So, therefore, now 27, which was earlier n to the power r, has become now only 10 possibilities, and you will see that if in this arrangements are something called n plus r minus 1 c n minus 1, where n is the number of cells and r is number of balls. We will discuss this one a little bit more detail later on, because this is very important, and we will come back to that. For the time being, we just wanted to show you how it looks. You can read this. So, what is the number of microstate? What is the number of such microstate of R? So, exactly. So, that is what I was saying, right, like how many microstate we can get when there are R indistinguishable ball and N. What is the number of such microstate when there are indistinguishable balls and N distinguishable boxes? So, this number of boxes will be N and number of balls should be R. In that case, you can see that it will be this formula, and we will come back to that later on. Now, let us simplify it even further. Let us make both balls and cells and boxes are indistinguishable. What will happen? So, I take 3 indistinguishable ball and 3 indistinguishable boxes. So, I have 3 indistinguishable ball and 3 boxes. You see, I have not labeled the boxes anymore. So, they are indistinguishable boxes, right. These situations, again I can say that this is star and boxes are, of course, it does not matter whether it is 1, 2 or 3 or not. You can see it reduces only to 3 possibilities. For example, I showed you earlier that if balls were distinguishable and boxes were distinguishable, this would correspond to 6 possible configuration. Now, that is only 1. I showed you here also that this, so if balls were distinguishable, this would be 3 possible configurations, and when both were distinguishable, this had many more configuration. This situation 2, 1, many more configurations. But here it is either all the 3 particles in one box or not, or there is 2 particle and 1 particle situation, or there is 3 particle situation. It is almost like I am breaking my 3 into these situations. I am breaking my 3 into 3 0 0 or 2 1 1, sorry 2 1 0 or 1 1 1. Now, what will happen if I have R indistinguishable ball in N indistinguishable cells? Now, how do we get R indistinguishable ball in N indistinguishable boxes? So, this is again something that I have to come back later on, but I will just give you a glimpse of it. It is called integer partitions, partition of an integer. We will briefly discuss about that, however, it is not so important for this particular course. This is just to give you an idea, if you are curious enough, that in a situations I have, let us say, 11 indistinguishable balls and I have to break it into 3 indistinguishable boxes, how many such thing will come up. And also you will see these 3 situations are kind of 3 different distributions, and each of them will have its own microstates when the balls and boxes will be distinguishable. We will come back to that later on. It is just to give you an idea that how the ball can be put in the boxes and what if they are indistinguishable or distinguishable. The reason is that you will see that the classical particles are typically distinguishable particles, whereas quantum particles like electrons, protons are indistinguishable particles. So, therefore, while calculating the statistics, we have to consider whether the particles are distinguishable or not. For example, when we do classical statistics that gives us Maxwell-Boltzmann statistics, we need to consider particles to be distinguishable. If we calculate Fermi-Dirac or Bose-Einstein statistics, which come from quantum statistics, which are called quantum statistics for a reason, and there you will see that the indistinguishability of the particle will come into the picture, and also the restrictions whether there can be one or more particle in a box, that also gives rise to new statistics. The point is that we can always consider or calculate the statistics whether the particle is distinguishable or not. That is okay for us to do so and get different numbers, but we have to always check with experiment that what we are getting out of that experiment. If our experiment matches with the theory that requires indistinguishability, then we will know that they are indistinguishable. For example, we looking at a glass of water, we cannot distinguish it from one water to another water. Even if you use microscope, we will not be able to, but our inability to distinguish a particle has nothing to do with the statistics that experimentally comes in, because that means the distinguishability inherent in the system or in the particle such a way that giving us a statistics that correspond to indistinguishable particle statistics. So, that is an important point. It is nothing to do with our indistinguishability, it is to do with the indistinguishability that is inherent to the system, or looking at the statistics that is coming out of the experiment, and that is what is more interesting to note. Now that we go over this balls and boxes situation, let us see what happens when we calculate only calculation of 2 level systems only.